Hey everyone, welcome to 3.7 optimization. It's one of the most common uses of calculus is actually optimization because it helps businesses find the max profit or the minimum cost, or if they're trying to make some sort of object or figure or shape, I don't know, whatever they're trying to make. They're trying to maximize things or minimize things, so we're trying to do a lot of logistics deals with this kind of stuff. So if you ever heard logistics, UPS, trying to figure out the shortest distances and all that kind of stuff. All this is going to be really important. So we're going to jump right into this example, and the boxes that you are trying to make, there is one exact size that we want to be able to figure out will maximize the volume. Alright, so we know it's got a square base, and we know the surface area has got to be 84 square inches. So we're going to have two equations, one is volume and one is surface area. We know our volume is going to be x squared h, because x squared is that's our base, and h is the height. Alright, so we have base times height equals our volume. And then surface area is going to be x squared plus 4xh equals 84. And you say, well, where'd you come up with that? Well, this is the base, or the bottom. And these are the four sides. Remember, we're not making a top, so that's really it. So we've got the base plus the four sides is going to equal this 84, because that's how many total square inches we have to make this out of. Okay, so I've got two equations. I've got an x and an h. I don't really want to be able to use both, so what we're going to do is we're going to try and solve for h in this equation. We're going to still have x's, but that's okay. So what we're going to do is really going to forget about that s. We're just going to use this half of the equation. And I'm going to subtract x squared and divide by 4x, so that way I can say h equals 84 minus x squared all over 4x. Alright, if you're not really sure how I do that, just follow along and figure out, oh yeah, subtract x squared, divide by 4x, and I solve for h. So then what I'm going to do is I'm going to take this and plug it into that equation, and we should get volume equals x squared times 84 minus x squared over 4x. Close my parentheses, and I've got it. Right? I'm going to clean this up a little bit to make it a little bit easier for what I'm going to do next. Distribute the x squared in, I should get volume equals x squared, I should say 84x squared. I'm not even going to do that. Hold on. I've got a better way to do this and make it a little bit faster. I'm going to cancel out this x and this x. That way I'm left with, that's what I'm looking for, x times 84 minus x squared over 4, which then I can finally write down as, I'll move this up just a little bit, 84x minus x to the third all over 4. And finally, I'm going to write that as the volume equals 84 divided by 4 is 21x minus 1/4 x to the third. Now, I could write it as 1/4 x cubed or x cubed over 4. Either way, it doesn't really matter. So you might see them in slightly different ways. All right. So what we are going to do next is let's just go through, and you can see page 206 for strategies in a little bit, but let's finish this one first. So we had, again, it was volume equals 21x minus x cubed over 4. So when we're trying to do optimization, really what we're trying to do is find the max or min, right? You say, okay, max or min, how do we find that? We've done that before, right? We did that with the first derivative test, the second derivative test, all that stuff we've been doing in Chapter 3. We're trying to find the max volume. So if we can find the x, so if we have x and y, what x value gives us the maximum volume? That will give us what size base we need to make to maximize the volume. Alright, so in order to do that, let's find the derivative of v with respect to x, and that's going to equal 21 minus 3/4 x squared. I don't need to do dx over anything because we're taking the derivative with respect to x. Alright, so that's my whole thing, and remember, if I want to find max or min, I need to find the critical numbers is when the derivative is set to 0. So then I can solve this, and I can say that's 21 equals 3/4 x squared. Multiply by 3/4 or 4/3, and you should get 28 equals x squared. So that means the square root of 28 equals x, and it should be plus and minus, but we know it can't be negative because we can't have a negative side length. So I know that x can equal square root of 28 is a possible one. Now, if you go back to Raleigh's theorem and the mean value theorem, remember that critical numbers could also be our endpoints. So we have to check endpoints. So you say, okay, well, where are endpoints? What do you mean? Well, what's the smallest x could be, and what's the largest that x could be? Well, we know that the smallest x could be, we could say x has got to be 0 if we don't have a base, so that's probably not going to be our box because we don't have a base. We're probably not going to have a box to make, right? And the other one is, we know that 84 is our surface area, right? So If 84 is our surface area, that means that x, if the whole base, if we don't have any sides at all, we just have a base and it's just that sheet of paper, that could also be our whole part. So we could say that x could equal the square root of 84, right? If we don't have a top, it's not going to work out. But you say, well, why do we have to check those? Because sometimes that might be the case. It may not be for the box. I mean, it doesn't really make sense. I'm guessing this is probably going to be our answer. But still, get in the habit of checking those endpoints, and that's why we're doing this example. Okay, so I want to check x is 0, x is square root of 28, and x is square root of 84 into the original function. That way I can figure out what x and y are going to be, because I can say one of these things is going to be the right base. What's my volume? Because I want to find the max volume. So I can say check the equation, which was for volume, it was v equals x squared, or actually we can do this a little bit easier. v equals 21x minus x cubed over 4. So I just have to plug these values in for x. Okay, so what I did with my calculator already to make this go a little bit faster is I have my equation already in there. So I could go to the graph, I could do all sorts of things, but you know what I did instead? I had my table start at 0 so I can check my first point at 0. And then I had my change in table go up by the square root of 28, so I can check those two right away. So the first two values, which makes sense, right? 0, 0. So I know that 0, 0 is a solution. I got to check that one. And my next one is the square root of 28 and 74.081. So I can say square root of 28 and 74.081 is another point. And then I'm just going to go back to my table and say, let's just start at the square root of 84. I'm letting the calculator do the work for me. And the square root of 84, oh, look at that. It's 0. That's a good thing because that means I did this right. Square root of 84, comma 0. So, oh, there we go. You couldn't see all that. I'm sorry. So you could see that 0, 0, square root of 84, 0 are possible ones, but they're not maxes. They're actually probably minimums for this case. That means this one right here, square root of 28 for x, is going to be our maximum. So we say, okay, what's the square root of 28? Well, I actually have it here. It's about 5.29. So 5.29 is going to maximize that area or volume of this box. So when we're going through these, see page 206 for some strategies. And finally, what I would like you to do with their extra sheet of paper, please make the best box that will maximize our volume. All right, good luck.